So, picture this. You've designed a radical new jet, one that takes off vertically, kind of like a helicopter. Before you spend millions or maybe even billions building it, how do you know if it'll even fly? You can't just put it in a normal wind tunnel, right? You need to fly it without actually flying it. This was the exact problem staring down the DuPont Aerospace Company. They were building this revolutionary vertical takeoff jet, and they needed a digital proving ground. A virtual wind tunnel to test its stability and control systems in real time, with actual hardware plugged right in. So, what kind of software engine could possibly power a task that demanding? So yeah, how do you create a simulation that's so realistic you can bet a multi-million-dollar prototype on it? What's the secret engine running under the hood of these incredibly advanced virtual flight tests? Well, the answer is a piece of software called JSBSim. At its core, it's a flight dynamics model, or an FDM. The best way to think of it is as a pure physics engine for anything that flies. And let's be clear, this is not a game. It's a C++ library that just crunches numbers. It's calculating all the forces, lift, drag, thrust, to figure out exactly how an aircraft is going to move, moment by moment. So in this explainer, we're going to break down how this incredible open source tool really works. We'll look at its real-world impact, see how you actually describe a plane to a computer, uncover the secret sauce to its real-time aerodynamics, and hey, we'll even build a simple autopilot from scratch. First things first, let's get one thing straight. JSBSim isn't just for hobbyists. No, this is a serious tool. It's used in academia, by governments, and in some really high-stakes industrial projects. I mean, just look at this list of users. It's pretty impressive. Aerocross uses it for what's called hardware-in-the-loop testing of their UAVs. MITRE uses it to study air traffic control patterns. The University of Naples actually powers a full-motion flight simulator with it. And get this, the U.S. Department of Transportation even uses it to build mathematical models of human pilots. So yeah, this is not just a game engine. It's a professional-grade simulation toolkit for sure. Okay, so how do you even get started? How do you take a real-world aircraft and turn it into a bunch of data that a computer can actually understand? Well, it all starts with what I like to call the aircraft's digital recipe. It all begins with this digital recipe. First, you've got to define the basic metrics, the physical dimensions, things like wingspan and tail area. Second, you specify its mass and balance. What's its empty weight, where is the center of gravity, and what are its moments of inertia, which is just a fancy way of saying how it resists tumbling. And finally, you define how it interacts with the ground, exactly where the landing gear is and how its springs and shocks behave. And this part is absolutely key. All of this info gets fed into JSBSim through simple text files using XML. See, we're not building a pretty 3D model that you'd see in a movie. We're creating a digital twin based on hard engineering data. We're defining the very soul of the aircraft. Okay, so we've got a static blueprint of the plane, but how do we actually make it fly? Well, that means we have to model the incredibly complex forces of aerodynamics. And this is where JSBSim has a really clever trick up its sleeve. Now, this is where it gets really interesting. The hard way to calculate lift would be to try and solve these insanely complex fluid dynamics equations for every single frame of the simulation. Your computer would just grind to a halt. The JSBSim way is way more elegant. It uses something called the coefficient buildup method. Basically, instead of calculating from scratch, it uses data that's already been calculated from real wind tunnel tests or other flight data. All of that data is stored in simple lookup tables, just like this one. So for any given angle of attack, which is just the angle of the wing to the oncoming air, the computer can instantly look up what the lift should be. It's fast, it's efficient, and most importantly, it's based on real-world measurements. This is the secret that makes accurate, real-time flight simulation possible on a totally standard computer. All right, we have the plane, we have the physics. Now let's put it all together and actually build a control system. Let's teach our virtual plane to fly itself. So the classic first challenge for any autopilot is the wing leveler. The goal is super simple. If the plane rolls to one side, the autopilot needs to automatically use the ailerons to bring it back to a roll angle of 0. So how would we build that logic in JSBSim? We build it up in 3 stages. First, we try proportional control. The bigger the roll angle, the more aileron we apply. It's simple, but it never quite gets back to 0. There's always this annoying little error. So to fix that, we add integral control. Now the system looks at the error over time and adds a correction to kill that persistent bias. Okay, great, now we can get to perfectly level, but we tend to overshoot and wobble. So the final piece is adding derivative control. This one looks at the rate of change, letting the system anticipate where it's going and smooth everything out for a stable, precise flight. And this whole PID, or proportional integral derivative logic, well, it's not just for airplanes. This is the fundamental building block of countless control systems you use every single day, from the cruise control in your car to the thermostat in your house. So, the crucial point here is this. JSBSim isn't just a flight simulator program. It's a flexible, powerful, open-source toolkit. It gives engineers and students and researchers a set of building blocks to model, test, and understand the complex physics of flight, or really any other dynamic system they can dream up. And that really leaves us with a fascinating thought, doesn't it? If a community of open-source developers can create a tool powerful enough to realistically simulate a complex jet on a simple laptop, what's next? What other incredibly complex systems, maybe from climate models to economic systems, will we be able to accurately model and understand tomorrow?